Okay, today we're actually going back a chapter to section 5.4, and we're going to talk about something we didn't discuss in the first part, which is the net change theorem. So some applications to do with antiderivatives, where we're calculating the net change in a quantity. Okay, so let's first to say what the net change theorem is. Let's say you know the function that represents the rate of change in a quantity. So let's say you know f prime of x, and we'll see some examples of what that could mean. But if you know f prime of x and you take the integral of that, remember the integral is the opposite of the derivative, so it cancels it out, and it gives you what the function is at b minus the function at a, because those are the two bounds here for the integral. So that's essentially the net change in the quantity between b and a. So let's look at some examples, and I think it'll become more clear there. Okay, so let's say we have a water tank. V prime t is the rate at which the volume of water in the tank is changing at t hours. Then what would this integral represent? So remember the integral and I'm going to use my cursor or writing today, or typing. V prime t represents the derivative, or like how fast the water is changing, but that's going to cancel out with the integral. They're opposites of each other. So we're going to get, actually I'll write something first. We're going to get v of 10 minus v of 0. So the volume at 10 minus volume of 0. It'll give us the net change in the volume of water between 0 seconds and 10 seconds. Or sorry, hours. Yeah, hours and 10 hours. Or you could just say in the first 10 hours. Okay, so the bounds tell you the time, and then you'll always have the derivative in the interval there. I'm just going to change it to blue. Okay, cool. So let's look at this one. P prime of t measures the growth rate of a population of rabbits at time t, years since 2000. Then the integral from 2 to 5 of p prime t. Remember, this is going to cancel out the derivative, so the integral and the derivative kind of cancel each other out. So it'll end up giving us p of 5 minus p of 2, which would be the change in population from year 2 to year 5. So the net change in population so it starts at year 2000. So year 0 is 2000. So it's between 2002 and 2005. Okay, so it'll tell you how much the rabbit population went up by or decreased by. It doesn't tell you the rabbit population. It tells you the change in the rabbit population over that time period. Same with this water volume thing. It's just telling you the change in the water volume. It's not telling you the actual volume of water. Okay, so let's do some examples where we actually do some calculations. This one is a physics one. A particle moves vertically, so that's velocity. Remember, the velocity is actually the derivative of the position function. That's important here. So it's how fast the position is changing with time. Find the displacement of the particle during the first 3 seconds. So this word displacement in physics, it just means, I'll put it here, net change in position. So we're just using the net change theorem for this first part in the first 3 seconds. So I'm going from 0 to 3, and I'm going to do s prime of t, or v of t, dt, to get the net change in position. So it'll be from 0 to 3, and we actually have the function this time. We can actually calculate it. So it would be, we're going to bump the power up and divide by the power. So it'll be t cubed. 3's will cancel out, minus 12t. Oops. And I'm assuming we've done a lot of practice with antiderivatives here, so I'm not going to go into too much detail on actually how to calculate it. But you should get -9 if you plug those in. So let's write that in a sentence. Oh, maybe I'll just write it out. the displacement is 9, so we're talking about meters here, in the negative direction. So in this case, it's downwards, because it says the particle's moving vertically. So the particle, from where it started, the particle ended up 9 meters below where it started. It doesn't say where the particle is at 3 seconds. It says that compared to where it started, it's 9 meters below, okay? Part B, if the particle started at position 2 meters up, what's the position at 3 seconds? So we know it started at, so we can take where it started, 2 meters, in the positive direction, and then we're going to add on the net change. We know we ended up 9 meters below where we started, -9. So then we would end up at -7 meters, or 7 meters in the downward direction. Okay, and then finally, find the total distance traveled during this time period. This is where we're going to need this graph. Distance and displacement are different. Distance doesn't have a direction attached to it. So when you're calculating distance, you need to take into account, you need to kind of separate out the parts where the particle was traveling in the negative direction and the parts where the particle was traveling in the positive direction. So when I'm looking at this velocity time graph here, remember all these numbers here represent, that I'm highlighting, represent the velocity at certain times. Now, when the velocity is negative, the particle is moving in the downwards direction. So that's happening between 0 and 2 seconds, all of these parts of the graph here. The particle has a negative velocity. And then after 2 seconds, the particle starts to have a positive velocity and it's moving in the positive direction. So we want to find the total distance traveled. So we're going to separate it out into the part where it's traveling in the negative direction, so downwards from 0 to 2 seconds. And then upwards from 2 to 3 seconds. Remember, we're looking at the time interval 0 to 3. So let's calculate the integral from 0 to 2, d of t dt. So it's going to be, it's the exact same antiderivative again, so I'm not going to go into that in detail. But this time it evaluates to 8 minus 4, -16. So in that first blue part there, the particle travels 16 meters downwards, okay? The negative represents the direction. So it travels 16 meters in the downwards direction in the first two seconds. Now let's look at the upward direction. So from 2 to 3, d of t dt, exact same antiderivative again, just evaluated at different bounds for the integral. And when you plug that in, you get 7. So in this little portion here, between 2 and 3, the particle travels 7 meters. So in total, the total distance the particle travels, and again, we don't care about the signs for distance, you're just adding up all the distances it travels. So we don't care if it's going in a negative or positive direction. So the total distance would be 16 meters plus 7 meters equals 23 meters. If you added those together with the signs, you would get -9, which was our answer in part A. But if you just care about the distance and not the direction, you get 23. Okay, so that's how I'd recommend doing that question. If you have that in your assignment, just separating into the downwards and upwards. And really the best way to do that is by looking at the graph, and I'll provide the graph for you on a test because I'm not going to be concerned with can you graph at this point. I just want you to be able to interpret the graph. So I will provide the graph on those types of questions, and then you just need to understand that you need to separate it into this blue part, the downwards direction, and then the yellow part, the upwards direction. Okay, and that is the end of the lesson. I will pause the video there.